Alright guys, so I guess this is recording. So since last time I think we're doing a problem, but I think I run into some issues, so maybe let's just go and restart the problem, okay? But I'm going to go a little bit faster with this. So I think the problem we did was problem 514. So if you want, I'm just going to retake the number from there. That way we don't waste any time. Okay, so this will be, maybe I forgot to do this, ES 305. Today is 4/10/18, and this will be lecture 19. Alright guys, I'm going to go a bit faster here because let's see if we can get this done. So this was a problem we're doing. We're basically there is a power cycle which is connected to a heat pump cycle. So what is the role of the power cycle? Is to create work, no? So we can say that the work created by the power cycle goes inside the heat pump cycle, which requires work. And basically what they say over here is that there is like a reservoir over here, at a temperature TD. Okay, so this one, there is Q1 over here, there is Q2 over here. If this is a QS over here, and then what else we have? Looks like there's some reservoir here at the bottom, Q sub naught. Reservoir at the temperature T naught. Okay, and what they're asking us is to find Q1 plus Q2 over Qs in terms of Ts, Td, and T0. So if you think about it, what are they really asking you to calculate? What is Q1 plus Q2 over Qs really is what? Physically. What was the definition for the efficiency? Do you remember? Is whatever we get out, no? So what are we getting out over here? Q1 and Q2 divided by what? Divided by what? By whatever we put in, no? The Qs. So really over here what they're asking you is to find the efficiency of what system? The one that is the power cycle plus the heat pump cycle. Okay, so we need to find that in terms of Ts, Td, and T naught. Alright, so maybe over here the first thing I'm going to do is that, so let's try to find one equation. What would be the expression for the work? If you look at the work, what is common between those two cycles, the power cycle and the heat pump cycle, would be the work. So what would be the work for the power cycle? Would be basically, what is the hot reservoir over here? So it's what? QS minus Q1, no? For the power cycle. Now for the heat pump cycle, what would that be? Be careful here, remember it's different, so what would that be? Which one is the hot one this time? So it's Q2, so the power will be equal to what? Q2 minus Q0, no? Yeah? So I can rearrange this. I'm just trying to find out equations. Q1 plus Q2 equal to QS plus Q0. So let's say that's our equation A. Okay, I'm going to write down first all the equations we can write down, and then we combine them. So I did this for the two cycles. Now, if I just look at the power cycle, we can do it in a different color, which is fine. What is the efficiency of the power cycle? Okay, I can go a bit faster. It will be 1 minus what? Q1 over Qs. And since this is reversible, that means this is equal to what? 1 minus T1 over Ts. Okay? So remember what we did. So now I could just come and look at this side over here of the equation. So what do you have? You have the 1 cancels out with the 1, the minus with the minus. And you end up having what? Q1 over Qs equals T1 over Ts. Okay, so what I'm trying to do is rewrite Q1 in function of the other one. So this will give you what? Q1 equal to Qs. Okay, I'm kind of follow what we did last time. Yeah, what's your question? Is TD. Yeah, TD. All right. Because T1 is TD, you're right. So this will be TD over Ts. Let's say that would be our equation Roman 1. Okay? We kind of did something similar last time. So I'm replacing the pages. That should be page 105. Maybe no. Let's just follow, because I think I scanned them, so it's gonna become. I'm gonna get confused. So 108. Okay, so let's just restart. I think sometimes if I try to rework it out from somewhere, I know I'm gonna get confused myself. Okay. I think I have it pretty clear now. I think I look at it. Hopefully I don't get. So we have this. I have a pretty good idea now, but we'll find out. So now I look at the power cycle. We do the same thing with the so let's do the same thing now for the what? For the heat pump. So for the heat pump, again, we need the figure. I think the letter we used was gamma. So what is the efficiency of the heat pump? We need to look at the top. So what are we getting out of the heat pump? This is a good review. Q2. So if you want, we can do it this way. What are we putting in? The work, no? So this will equal to what? Q2. What is the amount of work we put on this one? Q2 minus Q0. Okay? So this look at, so this will be equal to what? So I have to do the mistake again. So so this will be equal to what? T2, which is TD minus T naught. Okay? So if I just look at these two, so I do the inverse for both of them, so I can say that Q2 minus Q naught over Q naught will be equal to what? TD minus T naught over T sub D. So this will be equal to what? Will be equal to Q2 over Q naught. Alright, so it will be equal to Q2 Did I do the mistake? Yeah. That's why I was getting confused here. So see, I'm going too fast again. So this gives you 1 minus Q naught over Q2. So I will stop over here for a second. 1 minus T naught over TD. And let me know if you have any question, okay? Sorry for that. So now can cancel the minus sign, the 1, so that we have Q naught over Q2 equals to T naught over T sub D, and from here we can get that Q sub 2 will be equal to what? Q naught TD over T0. Okay, so I'll show you what I have in mind. Initially, I'm trying to replace this Q1 and Q2 into this equation, no? So we only have everything function of QS and Q naught. And see what happens. Okay? So now I'm going to replace I and double I into this expression and see what happens. So substituting what do we have? What is A? Is Q1 plus Q2 equal to QS plus Q naught. Yeah, I think I got it. Yeah. Okay, so what is Q1? From this equation is what? QS TD over TS, no? And what is Q2? Is Q naught TD over T naught. And this is equal to QS plus Q naught. So now, for example, I could factor out by QS. So I will get what? TD over T sub S minus 1. I'm moving this one to to the left hand side will be equal to Q naught factor of 1 minus TD over T naught. TS is the one from this reservoir over here. Oh no, this is TS is this one. You're right, TS is not a, is the one of the hot. So it wasn't on the figure. Yeah, you're correct, you see? Okay. So now, yes. Formula, which is this one, Q1 plus Q2 equal QS plus Q sub naught. Oh, you're welcome. Yeah, I know, when you go with the thick marker, it's not that easy. So if you have any questions, okay. So now, let me look at the first equation here. I need to do over QS. So this will give us Q sub naught Q sub S will be equal to what? TD over TS minus 1 divided by 1 minus TD T sub naught. Okay, so now I think you will understand what I'm trying to do is that from equation A, equation A is what? Is Q1 plus Q2 equals to QS plus Q naught, no? Yeah? So when I was trying to solve this problem, I was all the time looking at this expression because what are we trying to solve? The efficiency is Q1 plus Q2 divided by QS, no? Alright? So if I use that expression, we can say what? So that the efficiency, which is Q1 plus Q2 divided by Q sub S will be equal to what? Q sub S plus Q sub naught divided by Q sub S, and this will be equal to what? 1 plus Q sub 0 over Q sub S. Okay, so now what is that ratio? Is the one we just calculated in function of those temperatures, no? So I'm not going to simplify it, so at the end we have that Q sub 1 plus Q sub 2 over Q sub S will be equal to what? 1 plus TD over TS minus 1 minus T naught. Okay, so you see these problems are not, I'm not going to say not difficult, but they don't really ask you to do anything new, but they are not that clear what they ask you to do, okay? I think they're a little bit abstract. So anyway, let's keep done with this. So at least we've done this one's done. And let's go to new material. So lecture 19. The last things we did over here. I know where I need to go. So this will replace by that. Okay. So this goes together. So let's see what is the last thing we did over here. Okay, here we go. So we did cover this, we did cover this, and these are the problems. Alright, so I'm going to pick it up from here. So recalling. The Clausius inequality, which is what? That if we look at the ratio of delta Q over T over a cycle, that's why I do like a closed cycle, what were the two choices we had? If this ratio was equal to 0, that was meaning that the cycle was what? Reversible. And if it was negative, it means that it was irreversible. Okay? So this is what was known as the Clausius inequality. Okay, so this part gets a bit confusing about the entropy. Is that now we're gonna write down that Kelvin proposed the concept of increasing entropy of the universe. Increase in entropy of the universe. So what does that mean? Is that the total entropy higher or equal than 0. So saying that, you will have delta S of your system plus your delta S of the surrounding will always be larger than 0. And in most cases, this will mean that delta S of the system plus, let's say, delta Q over T should be higher or equal than 0. Okay, so this is concept of increasing entropy of the universe. Surrounding. Yeah. So basically surroundings can be what? Can be given temperature, you can be losing temperature to the surrounding, no? At a certain temperature. I know this gets a bit confusing because we go here from negative, then we come positive, but with the problems, it becomes pretty clear. Alright, so this concept, for example, now we can go to philosophical theories. So, the other day we said that the entropy, what is the entropy? What is a physical explanation of the entropy? So how much energy we are losing or wasting, no? So the more the entropy increases, that means the more energy we have wasted, no? So basically that concept over here means what? Is that the more stuff we do and the more energy we waste, what's going to happen at the end? The entropy of the universe is going to increase, okay? Up to a point that is not going to be more energy, more useful energy available, no? Okay? So when all energy is wasted and cannot be used anymore, is something that can, it can be also understood as that's when the universe will explode, no? Okay? I mean, it's like those black holes. What do? They absorb energy, but do they do anything with that energy? We don't know, but basically that's what it means, is that it's saying that we are wasting all that energy over there. Okay? So, entropy, I agree with you, is one of those terms that is not 100% understood and people use it for whatever they want, okay? Lately there's a theory, it's not a theory, the guy has some type of example, but for example, he tries to explain the evolution of the world from the entropy, okay? So basically, he says that, I don't know if it's true or not, but it's a theory, okay? That, for example, if you put two different molecules, all right, together, all right, there is no, by any, there is no physical law or any reason why those two molecules will go and try to combine together to create some type of living organism, no? Yep. Okay, you can put molecules, they can stay separate forever, no? However, if you do some experiment, you will find out that if you put two things together, two type of molecules together, they will try, I'm not going to say always, but they will try to combine and create something new. Okay? So if you look at it from the entropy point of view, what are they trying to do? Are they trying to waste the entropy, or are they trying to use the entropy properly? They try to use the energy in a way to form something new, no? Okay? So there is an old stuff, which I mean it's pretty new. I think it's a couple of years old, so it's probably not in the textbooks yet. But there is one guy that is trying to do like an evolution theory based on entropy, no? Saying that the microorganism by nature will try to always reduce the amount of entropy by combining together and to form new living molecules. Okay? So as I mentioned, for entropy you have all tastes and flavors. So we have this. Okay. Now we go to the important equation. It's not that this is not important, but the important equation comes now. So alright, so recalling the first principle of thermodynamics, which is what? Heat plus work equal to change in energy. Or I'm going to rewrite it, really this form is more appropriate, delta Q plus delta W equals dE, the differential of energy. Okay, so we have this. We got this one, A. So recalling the principle of the first principle of thermodynamics and the definition and defining, because we haven't done it, delta Q over T is going to be equal to the change in entropy. So let me just rewrite this, or delta Q over T equals S, where S is the entropy. So again, so this is the first principle of thermodynamics. I put it delta Q's because it's easier to understand, but you put Q plus work equal change in energy. So that was the first principle of thermodynamics. What was the deficiency of that equation? Or what were the deficiency of that equation? Basically we had two, is that we say that for a cycle, so the change of energy is 0 will mean that delta Q equal to minus work, so it means that you can transform all the work into heat or the heat into work. And we know that all those cycles are not 100% efficient, but we have those coefficients of efficiency, no? That we know how to calculate. And the other deficiency was that not all the cycles are reversible. So basically we gave the example, it's not the perfect example, but you can go from liquid water to solid water as ice, and back and forth to liquid water, okay, without major problems, okay? But if you burn a log of wood and it becomes ashes, then you cannot get the log of wood from the ashes. Alright? Okay? So we needed to define something to make it reversible or irreversible. So what is that stuff that is going to tell us that if something is reversible or irreversible? Is that ratio over here, delta Q over T, no? So now that delta Q over T, which represents how well you use the energy, we call it S to make things easier. So now we're going to combine those two equations. So how can we combine those two equations? What is the term that these two equations has in common? Q, no? Or delta Q. So we can say that delta Q will be equal to what? If we use this equation, will be equal to T times ds, no? So we replace this one into this equation now. Now that means that within this equation we have a term that we're introducing into this equation that takes care of defining if the system is reversible or irreversible. So 1, 1, 2. So let's say we have delta Q plus delta work equal change in energy, and we have delta Q over T equals ds. Okay, so from that equation we can write down that what delta Q is equal to T ds. If we go and substitute this one over here, generally I don't like to do those arrows, but for once we're gonna have what? Oops. So delta Q plus delta W over dE becomes what? T ds plus change in work equal to the change in energy. So that equation over here, you see, is not rocket science. The only thing we did was to use this equation and substitute one value, is what is known as the second principle of thermodynamics. Okay, so if you want, let's do a very quick summary, just to know the equations that we have so far. So we have what? Q plus work equal change in energy, or we can write that equation as delta Q plus delta work equal dE. So this is the first principle. Then we have the equation which is ds equals delta Q over T. So this is the first principle. This is the definition of entropy. And if you combine these two, what do you get? Second principle of thermodynamics. Okay, we're going to use this now, but just as a reminder. Let's see if you remember this. So what was the difference between the internal energy and the enthalpy? Do you remember that one? That would be equal to what? If we use remember this one or no? What's the difference between those two? That's important over here. Otherwise, you're gonna get lost. So it wasn't even that important until now, but now it becomes really important. But it's not the first time I mention it. Remember, we said that the internal energy will be in function of C sub V, and that the change in enthalpy will be proportional to what? C sub P, no? Yeah? Okay, so what is the difference between U and H? Let's see if you remember that one. What is U? U is the internal energy. What is H? Correct, so the internal energy is really internal energy plus work done by pressure, no? PdV, no? PV. Alright? Okay. So now we're going to derive something that is known as the TdS relations. And I think that's probably where we're going to stop today. Okay, so before I do that, maybe you have seen that I posted some homeworks. Okay, so, and I think next week is not going to be the last week of classes, but the following one, no? So my goal is to finish maybe this week all the class material. Maybe we need to do some on Tuesday, but to finish all the class material, maybe just work the last 2 weeks on homeworks and problems. Alright? Because here you have some, conceptual stuff that you need practice in order to really understand. Okay, so now we're going to do the TdS relations. So if you understand these derivations and know how to do them, okay, you are in good shape for this chapter, because really everything comes from this TdS relation. You need sometimes to modify them a little bit, but that's what they are. Okay, so I'm going to say, recalling the second principle of thermodynamics, what do we have? We have the equation TdS plus change in work equal to what? Change in energy. Okay? So now if I say neglecting kinetic and potential energies, what does that mean? Maybe let me do the detail. So D is equal to change in kinetic energy plus change in potential energy plus change in internal energy, no? But I still want to use the differential form, the D. So this will give us what? TdS plus delta work equal to delta U, or I don't like the delta for this, the TdS relation, TdS plus partial of work equal to du. So far, except for the TdS, nothing new, no? Okay? Now, what is the work done by the pressure? Minus PdV, no? So what would be the differential of the pressure if we take the delta? That's why I put the delta, that's the only reason, because it will be before the integration, no? So it will be equal just to minus PdV. That's why I changed the notation, just for this, okay? So this will become what? TDS minus PdV equal to du, or you will have TDS equals to du plus PdV. So here we got the first TDS relation in function of u. Okay? Now what we need to do is find the other TDS relation, but instead in function of u, in function of h. So how can we do that? What is u? Sorry, what is h? We can do with what is h? U plus PV, no? So I've never done it this way, but we can maybe do it this way. So if we do this, what will be dH? Let's see if it works. If you take the derivative, if you do the derivative of h, will be equal to what? Du, no? Plus what? What is the derivative of a function uv? Is u prime v plus v u prime, correct? So what will be the derivative of PV? Okay, so it will be what then? Let's say it will be P dV plus V dP. Okay? So if I take this equation here, so we have du will be equal to what? Will be equal to dH minus PdV minus V dP. So next, if we substitute du into that big equation A, what are we going to get? Maybe I can start over here and go to the next line. Let me go to the next page. So this will be page, what, 113. So look here at the equations, okay? So 114. So let me just rewrite it. Take TDS equals to du plus PdV. So we have what? TDS equals to what? Now we substitute the du, which is equal to what? dH minus PdV minus VdP plus PdV. So what happens over here? These two cancel out. So at the end we have TDS equal to dH minus V be our equation B. So, what are the two TdS relations? We have TdS equals to du plus pdv, and the other one is what? TdS equal to dH minus v dp. Okay guys, so let's go back for a second. How did we do all this stuff? We started from what's the name of this equation? Second principle of thermodynamics. Where is that equation coming from? We have the first principle of thermodynamics. We just replace the entropy equation. We say delta Q equal to TdS. We replace it over here now, and we get that equation over here. All right? Okay, is that something complicated to do? Well, it's not complicated, but you need to understand that. Now, when we do the TdS relations, what did we do? We just say now, neglecting kinetic and potential energy, we have what? TdS plus work equal to change in internal energy. All right? What is the work done by the pressure? So the work done by the pressure, W will be pdv. So I substitute TdS du plus pdv. This is our first one. Now we want to use H. So I write H equal U plus PV. I go through the derivatives and substitute and find this equation here. TdS equal dH minus VdP. So these are the two TdS relations. So these are general. We didn't say open system, closed system, ideal substance, or any type of substance, no? Okay? So the equations are very general. All right? So, however, so now let's say for an ideal gas slash ideal substance. Really is ideal gas, but it can be extended to ideal substance. So by the term ideal, here what does the term ideal really mean? What is specific about the gas? That's what we call ideal. That's important here, okay? Conceptually, this is the important part. What is something specific about the gas? What is the main difference, let's say, between a gas, air, and water? A substance. What is the main difference? Go ahead. The state, perfectly. So the air is always in the same state. Yes? So water can go to different states, but can I assume the water to be more or less like an ideal if, let's say, we just go from, let's say, cold water to warm water? It doesn't change state, no? Okay, it's just the temperature, just the same thing. You have cold air, you can go to warm air, no? Without changing the states. So if the equation works within one state for the air, maybe this should work for a substance if that substance doesn't change its state. Okay? Like let's say the water. If the water doesn't change the state, it can sort of behave, you can say it cannot behave a little bit like the air that cannot change its state. Okay? Alright? So in that case, so let's go to the next step. So if you don't change state, so the state of a substance is determined by what? By the properties. So if you don't change states, that means the properties more or less should remain more or less constant, no? Okay? So, for an ideal gas, what are the two equations we have? PV equals RT. Is this R bar or no R bar? I think it's no R bar. Is it R bar or no R bar? I think there is no bar. Okay, so this is the ideal gas relation, good. But the other thing is that if it doesn't change states, I think I wrote down this equation here. What could you say? Is that you could say that du would be proportional to what? I think we put over here. CV dt, no? Why? Because what is CV? CV is a property. So if it doesn't change state, it can be pretty constant, no? Yeah? What happened? Okay. What happened if it was changing states? Could you do this or no? You will have to do what? You will have no choice to do U2 minus U1 and go and look at the tables, no? Yeah? But if it is more or less constant, you can have CV times T. What about DH? Will be CP dt, or this will be, if it's not ideal, H2 minus H1, no? Yeah? So having these relations, let's look at the first one. I don't know what color to use anymore. So if we look at this relation here, TdS, the first one, TdS equals du plus P dV. Okay? For an ideal substance, we'll have what? du will be proportional to what? C sub V dt, no? Yeah? Plus, what would be P? If we use the relation PV equal RT, P will be equal to what? RT divided by V. So this will be equal then to RT. Now you maybe see what's going to happen. TdS divided by V. If you understand this, you're not going to have any problem, okay? But that's why we need some practice. So now, what happens if I move the T to that side? If I divide, if you want, both sides by T, what am I going to get? Change of the ds will be equal to what? CV times, and maybe, sorry for that, this should be C sub V, okay? I did it too big. C sub V, and this one as well is not C times V, C sub V. I don't want to create confusion. So C sub V times dt over T, and the second term will become what? Plus, what happened to the T? It will cancel out. You will have ds equals C sub V dt times dt divided by T plus R dV divided by V. Okay? So, next. Too many pages over here. So page 115. If I go and say integrating. What am I going to get? I'm going to get integral of ds equal to this way. So let's say we integrate. I just put the limits to give you. We don't need to put any values, but. So what would be the left-hand side equal to? Would be equal to S2 minus S1, no? Okay, what did we say is that if you don't change state, the properties are more or less constant. So CV, is it constant? We assume it's constant. So we could move it outside the integration sign. And what is the integral of dt over t? Natural log, no? Of what? T2 over T1. And now, what would be the second one? Would be plus R log of what? V2 over V1. Okay? Or you can say that the change of entropy delta S would be equal to CV log timeout for something. So plus CV log T2 over T1 plus R log T2 over V1. I should go and check if it's R or R bar. I'm pretty sure it's R, but might be R bar. Can I go check real quick because I don't want to give you an equation that is wrong. So computer. Oh no. I'm even. Well. I hope it didn't stop the recording. Anyway, so we are here. Introducing the TDS equations. So that's what we did. Okay, that we can do that after the compressible. It will be, yeah, incompressible dV is 0, but okay, for an ideal gas is R. Okay, I think we're good. So it's, see, we got the first one here. All right, we're good. So basically, you see, this corresponds to what? TDS equal to du plus PdV, no? Now this one will correspond to what? TDS equal to dH minus VdP, okay, or something like that, okay? So we derive this one. Let's see, now we have time to derive this one, and we stop right there. So so similarly, this time I do it in orange. We have TDS equals to what? dH minus V dP. I guess this one you can do it on your own. So let's see, what is dH? Cp dt, no? Yeah? And if we use the ideal gas relation PV equal RT, V will be equal to what? RT over P. So it will give you minus RT dP over P. If we divide both sides by T, what do you get? ds equal to Cp dt over T minus R dP over P. So if we integrate, so let's say integrating, we get ds equals to Cp dt over T minus integral of R dP over P. I do the same as before, S1, S2, T1, T2, but this time will be P1, P2. So this will give you what? S2 minus S1, which I'm going to call delta S, okay, to be a little bit faster, will be equal to what? Cp log of T2 over T1 minus R log P2 over P1. Okay, I think for today we're going to stop over here. Okay, so 1, 2, 3 things, guys. So first one, you saw that I posted homework. So on the homework, I think there's one due a week from today. In that homework, you have problems from the chapter 5, the ones like we did the last 2 classes, as well as you have some problems from this chapter, but only for closed systems. Okay, so these are the equations now. I'm going to derive, I'm going to rewrite, I'm going to try to use this for the closed system, okay, between next class and probably next class. Then Tuesday we'll use part of the task for homework, and then I will derive all the tasks for homework on Tuesday, and then Thursday I will use that class to define all these for the open systems, no? Okay? And I think you have a homework due then the following Tuesday. Okay, and then from there on, we just do problems about open system and closed system and prepare for the exams. Okay, there's not much more material than this. There's probably, I'm guessing, about maybe 5 more pages of class material, and then everything else should be problems. Okay? All right. So have a good afternoon.